Hi, welcome to this video on linear programming duality. In this video, we're going to see how to take the dual of a general linear program that's written as a maximization problem. So we already know how to do this in the case that the linear program is in standard equality form. We're going to see how we do this in more general linear programs now. So here is 1 and 2, and we're going to take the dual of both of these in this video. These are generalizations. In fact, 2 is even more general than 1, so all we really need to do is 2, but we'll do 1 as well as a warm-up to building up to 2. So 1 is a generalization of standard equality form because, well, you can see it's almost exactly like standard equality form, except that we have matrix inequality constraints here rather than matrix equality constraints. So we've relaxed the condition of equals to, and we've relaxed it to less than or equal to constraints instead. And so this encompasses many more linear programs in that sense. And 2 is even further generalization because we have matrix inequality constraints again, but now we don't even have the variable non-negativity constraints. You can see now we're allowing x to be free variables. So there's no explicit sign constraints other than whatever's imposed by the matrix constraints. And so this is actually the most general type that we can have. It's worth noting that we can encode variable non-negativity constraints or any other type of constraint on the x's, but we would have to incorporate those into the matrix A rather than explicitly writing them out separately. The difference is that with type 1 here, we were forced to have variable non-negativity constraints. With 2, we might still have them, but we don't need to. It's not necessary. They could be free. The only constraints are whatever's imposed by A, the matrix A, and the right-hand side. So let's see how to take the dual of both of these. We'll start with 1. So, okay, so we're comparing number 1 to standard equality form first. So on the left here is this new type 1, and on the right is standard equality form. So you can see the difference is the less than or equal to sign versus the equals to sign that we have for the matrix constraints. So let's just remember how we took the dual for standard equality form. Well, we looked at the matrix constraints, ax equals b, and then we took a linear combination of the constraints, which corresponds to multiplying on the left by a vector y. So y transpose ax equals y transpose b, and then we said that this y transpose b could become an upper bound on the objective function value c transpose x by imposing a constraint on y transpose ax here. We said this would be in turn greater than or equal to c transpose x as long as we enforce the constraint that y transpose a is greater than or equal to c transpose. If we enforce that, then y transpose b would truly be an upper bound on c transpose x. And so we can encode this as we're minimizing the upper bound b transpose y such that it satisfies the constraint. And I'll write it as a transpose y being greater than or equal to c. So I just took the transpose of, here I just took the transpose of this condition. But anyways, it's the same condition. So now b transpose y is truly an upper bound that we're minimizing. It's going to be very similar for case 1 here, but there's going to be a slight difference that we'll encounter almost immediately. So we're going to again take a linear combination of the matrix constraints. So we start with ax less than or equal to b, and so we multiply on the left by y transpose. So we have y transpose ax is less than or equal to y transpose b. But actually, you should catch me already and say that's not necessarily true, because now we have a less than or equal to sign rather than an equals to sign. And so when you multiply by some vector y, the direction of that less than or equals to does not need to be preserved after multiplication unless the thing that you're multiplying by is itself non-negative. Because when you multiply by negative things, that flips the sign of the direction of the inequality. So if you want to keep it the same, it must be that the thing you're multiplying by is non-negative. So, well, if you want to guarantee it, at least, it has to be, y has to be. So now we're enforcing y is non-negative. And again, we want this to be an upper bound on c transpose x, so that overall y transpose b is greater than c transpose x. And again, the way you enforce this this condition is to enforce y transpose A to be greater than or equal to C transpose. So if this is true, then when you multiply by the vector x, still the direction of the inequality will be preserved because we know that x is non-negative in this case. So these conditions that we enforce on the vector y will be sufficient to guarantee that y transpose B is an upper bound. So we can encode this as our dual linear program. So we're minimizing the upper bound B transpose y such that, so A transpose y, again, that's greater than or equal to C, but now we also must enforce that y is non-negative. And so this is the dual of 1. So the difference is simply that we enforce this y being non-negative, and that corresponds to the fact that that we have a less than or equal to sign in the primal matrix constraints rather than an equals to sign. Because when you multiply by a vector y, we didn't have to worry about any direction of any inequalities in the SEF version, because there was an equals to. So whether y was a positive or negative for each of its components, it doesn't matter, because an equals to sign is still an equals to sign. What you do to the left is what you do to the right. Then the end result will be the same. So regardless of what the signs of the things that you're multiplying by are. And that's in contrast to what we're doing now. We have an inequality sign, and so when you multiply by, when you're doing multiplication, if you want that inequality to be preserved, it better be the case that the thing you're multiplying by is a non-negative. So we have to enforce that extra condition now. Okay, so here is a comparison of the primal and dual for both for type 1 and for standard equality form. So here's 1 and here's standard equality form. And so this is the primal for each, and on the right we have the dual of each. So you can see that the difference is we have a less than or equal to versus an equals to, and then correspondingly that makes y non-negative, or it allows y to be free, depending on which constraint you had. So intuitively, you can just see now that a looser constraint in the primal requires a stronger compensating constraint in the dual. So we had a more relaxed constraint, ax less than or equal to b, and that forced us to have more constraints in the dual. Because when we had a stronger constraint in the primal, ax equals b, we could have a more relaxed condition on the variables y, which was that we could allow y to be free. And here we cannot. So that's the difference. Okay, so let's now take it a step up to this most general type of linear program that's a maximization problem. So this is 2. And it's just worth noting this really does encompass every linear program that can be written as a maximization problem, because if I do have any equality constraints, I can turn them into a greater than or equal to and a less than or equal to constraint, and then for the greater than or equal to constraint, just multiply by -1 on each side, and that'll give you an equivalent less than or equal to constraint. So now you just have twice as many less than or equal to constraints. And then, yeah, for any greater than or equal to constraints that you originally had, of course, you can just multiply by -1 to make them less than or equal to. So the point is that everything can be written as less than or equal to constraints, even variable non-negativity, if that were the case, but we're not requiring it, at least explicitly. Okay, so let's take the dual of this. This is probably going to seem a bit tedious almost at this point, or maybe not, and that's why we're going through it. What you do is you take the matrix constraints and you take a linear combination of them again. So we start with y, we start with ax less than or equal to b, and now we take a linear combination. Y transpose ax is less than or equal to y transpose b is what we want, but again, in order to enforce that, it must be the case that we enforce that y is non-negative, so that the direction of this less than or equal to sign is preserved after the multiplication by the vector y transpose. So that's the same thing that we just saw before. And And again, we want this to be an upper bound on C transpose X. So let's say that we want this. What we want is for this to be greater than or equal to C transpose X. So what did we do before? What we did before is we said that we enforced that Y transpose A was greater than or equal to C transpose. Okay, but this will no longer work for us, because here, if we say Y transpose A is greater than or equal to C transpose, and now we're multiplying by the vector X, we want this direction of this inequality to be preserved, but we can't guarantee that anymore because X is not non-negative. It's not required to be non-negative. It's allowed to be a free variable. And so we can't guarantee that the direction of this inequality stays the same after multiplication by X. So we actually need to enforce an even stronger constraint. There's no way to fix this inequality. So what we need to do instead is, instead of having this be a less than or equal to, we need it to be an equals to constraint. And correspondingly, the thing that we need to enforce is not that Y transpose A is greater than or equal to C transpose. We need to enforce that Y transpose A equals C transpose. So this is a stronger constraint that we need to impose, because now when you multiply by the vector X, so now you have C transpose X equals Y transpose AX. And it doesn't matter whether X had components that were positive or negative. None of that matters. It's what you do to the left-hand side is what you do to the right-hand side. That you always get that, of course. I don't need to tell you that. You know how algebra works. This is an equals to sign. So when you enforce this stronger constraint, that compensates for the fact that X had a more relaxed initial condition. But you need this. You need to have that Y transpose A equals C transpose. It does not work if you say Y transpose A is greater than or equal to C transpose. That is not sufficient. So to encode this, we are minimizing B transpose Y. So let's just take note of the fact that indeed Y transpose B, or B transpose Y, same thing, it still is an upper bound on C transpose X. So we were able to make that work by imposing these two conditions. So this is bigger than this, which is the same as this in this case. Okay, so B transpose Y is an upper bound, so we're minimizing that upper bound such that the constraints that we now impose are A transpose Y equals C, and Y is non-negative. So this is the dual of 2. So we impose non-negativity of the variables Y, corresponding to the fact that we have matrix non-negativity constraints in the primal, and we impose equality constraints, equality matrix constraints in the dual, corresponding to the fact that we had free variables in the primal. So we had to impose a stronger condition there. Okay, so here it is cleaned up, and we're comparing the two. So this is, again, this is 2. This is our most general linear program here in maximization of maximization type. So you can see that the correspondence of the data is the same as before. Coefficients of the objective function in the primal become, in the dual, they become the right-hand side components of the constraints, and then right-hand side component constraints in the primal become dual objective function coefficients. That is exactly the same as what we've seen every time when we've taken the dual. But the difference now is that we're seeing how what the relationship between the sign constraints on the matrix constraints are. With this less than or equal to constraints now correspond to variable non-negativity, and free variables in the primal correspond to equality constraints in the dual. So let me just explicitly write this last part out. We start with Y transpose AX basically each time. That's like our middleman, and this is in between. So it's either going to be less than or equal to, or exactly equal to C transpose X, and it'll also be greater than or equal to, or exactly equal to. Oh, I'm sorry. I'm writing this backwards, aren't I? This is B transpose Y on the right here, and on the left it's C transpose X. So this is what we're always trying to do. So first, let's take a look at these signs. So we have a less than or equal to sign here when this is for standard equality form. This is for SEF. And we can impose this by imposing the condition on the y, that Y transpose A is greater than or equal to C transpose. So if you impose that, then you get this less than or equal to sign. On the other hand, the equality, that's corresponding to this general form for 2 here, because now you need a stronger constraint corresponding to the fact that the x variables are free. And the way you impose that is Y transpose A equals C transpose. Then you get that this equals 2 is true. And for these, you have it's flipped in a way. So this up top now corresponds to 2, and this is because when you start from ax is less than or equal to b, now you need to enforce the constraint that y is non-negative. And in contrast, in standard equality form, which is where this equals to would come from, you just get this for nothing. You don't have to impose any constraints on the vector y, so y can be free in standard equality form, corresponding to the fact that we started with ax equals b. So yes, you can see this relationship between constraints in the primal and variables in the dual, and variables in the primal and constraints in the dual. So let me just draw that out. So we have less than or equal to constraints in the primal, and that caused the variables in the dual to become non-negative. And kind of vice versa, we had free variables in the primal, and that caused the constraints to be equals to constraints in the dual. And so you can see that more relaxed constraints in the primal corresponds to stronger constraints in the dual. The most relaxed thing you can have is a free variables, and so the strongest constraints you can have are equals to constraints. And kind of in the middle is less than or equal to constraints, and correspondingly you have greater than or equal to 0 constraints for the variables in the dual. So there's this really interesting correspondence going on between primal and dual, and so and there's kind of a symmetric relationship there too. So we'll investigate that further in future videos. But that's really all there is to say for this video. We've just addressed where the dual of a general linear program in maximization form comes from, and so this is it. So now we know how to take the dual of every maximization linear program after this video. So that's all there is to say for this video. Thanks for watching.